it's the last lecture, and it's a computational lab. So it's the third we are having together. And it's going to be on the VICSEC models and in general about the concepts we saw yesterday. So I uploaded the structure is going to be the same as the other times, okay? So I'm going to give you a handout, a PDF with some exercises. I'll try to go a little bit over the concepts and some parts of the code before you do it, and then I'm going to give you some time to try and code it up yourselves. So this is how we at Georgia Tech do these kind of things. I know that many people did do computational labs in different ways, but this is how we find it to be actually more useful for students. Rather than staring at someone coding basically stuff for you on a projector. So, as the other time, you're going to be given some snippets, but don't be too strict about details of the implementations, okay? So you're free to change stuff as you feel more comfortable. So if you prefer the usage of some data structure over some other data structure, for instance, arrays over dictionaries, I mean, feel free to not do what is written on the handout, okay? The only important thing is that you get the right result, okay? It doesn't matter. Coding is not the end. Coding is always just a mean to get something, okay? So did you find the handouts? Okay, great. So I'm gonna actually pull up the instructor version here, and I also in a few minutes I will actually upload the solutions so that if you're stuck with some bug you can check them out. But let me briefly go through the concept, okay? So we're going to be implementing a model for some voids. In fact, we're going to be implementing the VICSEC model, whose rules are, as we saw yesterday, each bird is represented as a vector, which is the vector of the direction where these birds are going. And they reorient themselves based on the average of what the direction of their of their neighbors are. And the neighbors are defined via whichever other birds are within a radius r of the focal bird. And then you update the direction for each of the birds based on this rule, okay? So essentially what you're gonna try to do is to produce some plots like this one. These are called quivers, where you plot at each point you have a bird at position x, y, okay? Well, this is new shock. So at position, this is y, this is x. At position x, y, the given sets of this position, you have birds, and again, they are represented by a vector, okay? A vector in the linear algebra sense of the x and y components. And the rules for the update are presented in page 3, okay? So section 2a. And are you with me? Are you still looking for the handout? Are you here? Okay, good. And essentially, you will be initializing the code with some initial conditions that are specified in the snippets, and then given xi t and yi t for each I, you're going to update their direction directly as an angle, okay? So this is an angle theta in polar coordinates, okay? And the update rule is this one. So essentially, you take the average vector in the neighborhood here. This can be a little confusing. This is essentially because the domain of the arctangent is between minus pi half and pi half. And so whatever has direction in the negative x axis needs to be, the angle needs to be shifted by pi. In practice, you will be using some functions in your programming languages that already do this for you, okay? So you're gonna be using a function which is called arctan2, and I think this is the Python function. I think the R function is called the same, okay? And the point is that this already gives you the right domain for the arctangent, so that you don't have to worry about this part. So if you're confused about this, just don't worry about it and just use the arctan2 function. This will deal with this problem for you, okay? And then you update the position. Again, in our simplified version of this model, all birds have the same scalar speed. And you update the positions of the bird based on this discrete time rule. So you basically just multiply the speed times delta t times the direction. So this gives you the update rule to go from t to t plus 1. You cycle over the birds and you cycle over t. In this sense, if you want, the loop structure of this code is similar to the one we did for the stochastic game in the last computational while. In the sense that you need to loop over time, you advance time yourselves. It's not an ODE integrator, and you need to cycle over all of the individual in the population. Okay, so for instance, so this is the solution, but I want to show this to you because this sometimes is very confusing, and I don't want you to be confused over essentially something that is not important. To get the theta, you just do the average of the y and the x's in your neighborhood, and then you use this function arctan2, okay? And the tricky part is here, is to deal with borders, okay, in this code. Some of you, I know that Pedro already started doing the other lattice model for the game theory thing, so you already dealt with the periodic boundary conditions. But I'm going to assume that you folks don't know about that, so let me just briefly explain this. So your space is going to be a rectangle, in fact a square, of, let's say, size L. And we are going to assume that we are modeling something in the bulk of the population, meaning there is going to be another rectangle L here, another, square L here. And essentially what you assume is that whatever is happening in the other parts of the space is a copy of what happens in this rectangle. This is a technique that is widely used in computational schemes in biophysics. It's used a lot in molecular dynamics because sometimes you cannot simulate the whole system when you have too many things going on. So you just simulate something that is typical inside, okay? Therefore, so in practice, what does this mean? This means that if you have a bird here, okay, and another bird here, basically, these birds are not as far away as the whole rectangle. In fact, you need to imagine that you have a copy, a mirror image of this bird here, and therefore their distance is going to be this one, okay? This is called periodic boundary conditions. Boundary conditions. Okay. So this is a little bit of, I think this is from where you're coming, from the arguments we've seen the other times, this is the real new thing, okay? So this is probably where you will find more challenges in this computational lab. So try to think about that yourselves a little bit, and then I'm going to give you some hints on how to solve this problem, okay? So essentially, why is this important? This is important for two reasons, okay? The first step is reorienting the direction, as we said. Let's say, let me actually draw another one for this. But this is fairly easy, all right? Once you understand the rules. So to reorient yourself, you just need to essentially change the direction based on the neighbors. The tricky part is to define the neighborhood here, okay? So you need to find, you take the list of all the other birds in the population, and you need to find all of the birds that are within R. This means is that if you have a bird here, its neighborhood is going to be this, okay? Because you have periodic boundary conditions. So this is the neighborhood of this bird, because you need to imagine that you are on a torus, we say, topologically speaking, in the sense that you need to imagine that this is like a donut where you wrap around the border of this rectangle. So imagine that this is your rectangle, okay? And this is one border and this is the other border. You need to imagine that this is something like this, okay? It's like a donut, okay? So now this border and this border are actually the same position, all right? And this is what you're doing here. So these and these positions are the same. Therefore, the vicinity of this bird, even though in your abstraction these birds seem far away from these points, since we're using periodic boundary condition, actually these points are close to this bird. So this can be tricky, okay? And the other reason why you need to remember this periodic boundary condition is for the update of the position of the birds, okay? Imagine that you have a bird that is going in this direction, and if you update the x and y's according to this rule over there on the screen, if it were to come on this point, it means that this bird is now here, okay? So this is probably new to most of you. So let me know if you're confused about it, okay? Are you confused? Who's confused? You're confused. Can you phrase the nature of your confusion? Or are you just purely, it's just a pure confusion, pure confused state? So, okay, let me go over it another time. In your model, you're gonna have a box, okay? The birds, you're gonna place the x and y's of the birds essentially in a squared space, okay, like this. But you need to ask how you want to implement the behavior at the border, okay? So at the border, either you probably had something similar with your chemotaxis project, but then there you have hard borders, okay? So you have that's called no flux boundary conditions, and that's when you model the whole system, and therefore you have an actual barrier at the border. In this case, you don't, because these birds are in the air, let's say. So, and what we are doing is that we are actually taking. So let me actually show you. Maybe it's easier if I hope I didn't. No. So. Okay, I don't have the YouTube video anymore because it's going to take me too long to find it back. But let's say that you have a big flock of birds, a huge flock of birds, okay, that are flying in all directions, okay. What we are doing essentially is that we are only considering a sub part of this flock, okay, in the center of the flock, more or less. This is the conceptual idea behind what we are trying to do right now, okay? So you don't have a hard boundary here. They are not physically constrained in a cage, okay? And you also don't want to model the whole system because it would be too hard computationally. Your computer would take too long to do it. So we are using this trick where essentially we are saying on average over many realizations, the neighboring boxes are going to be statistically the same as the box we are considering. So we are using this trick where we are saying, okay, this is on a periodic boundary. So we are saying that this position here is the same as this position here. Okay? So this position here, outside of the box, in your simulation, is going to be equivalent to this position here inside the box. Okay, where delta x here is delta x here. And the same goes for y, okay? This position here, delta y, here we're gonna draw an asterisk, is gonna be the same as delta y here, okay? So you're basically, well, this should be on the border actually, sorry about that. We are basically wrapping around the box x and y's around the borders, okay? So if you have a dimension L, and if your x position is L plus something, let's say that your position is, if your xi is equal to L plus delta x, this means that in your code you need to consider that the position is delta x. Okay? Which is this, okay? This is true both when you're looking for the neighborhood and when you're updating the position based on the rule, on the dynamic rule. So, let's see. Okay, I'm gonna give you a little bit of time to think about it. But if you're confused and you have questions, I think the best thing, yes, please. We lost that. Yeah, go ahead.
I don't understand why this position should be considered the same as this position.
Because I'm telling you that this is a rule that we are deciding to implement. And essentially what we are trying to do is that we are trying to model a situation in which the neighboring part of the space that we are not modeling explicitly because our computer could not handle it in a reasonable amount of time. Okay, this is the idea, okay? Then, of course, in the thing that we are going to implement today, you would be able to increase L, but you need to imagine the researchers do this kind of codes with millions of birds or interacting particles. So actually, you need some computational trick to keep the time, computational time small. So what I'm saying is, since we don't want to explicitly consider this part of the world, let's say, I'm going to arbitrarily say that this part of the world is the same as this part of the world. And the birds interact with their mirror images in this fake world, if you want. It's a very arbitrary choice, but it's very useful when you're trying to model big systems. Okay? I know it's confusing if you think about the fact that you want to model exactly the position of all of the birds of the flock, but that's not what we are trying to do. We are trying to reproduce with some code some statistical properties of what happens at the center of the flock. This is it's a little bit different than asking at each time point what's the exact position of every bird in the flock. There is a little nuance. And so the first thing you need to think about is how to loop around on the boys, let's say, on the birds, and how to implement this boundary condition to define the neighborhood. Okay? I am gonna let you think about it for a little bit. There are many possible solutions. There is one solution specifically that is the one that requires the least amount of code, but you can come up with whatever solution you feel like. Yes, please.
Can you come here for a second?
Sure.
So, when we're calculating the new direction, right, we're going to use the mean of the sign of the
Right.
the neighborhood, but the neighborhood does it include the bird itself, the one that
Doesn't think the bird itself. So you can do both things. It's a modeling choice. You can either choose to consider the bird itself, so you consider himself, or not. We are going to be consider himself too. Yes. But the other possibility is also a viable modeling choice. It's totally reasonable. So this first question is not asking you to implement the whole code with the initial condition. It's basically only asking you to write a function that, given one bird that has position x, y, and direction theta, writes the reorientation rule, okay? Sorry?
But to write this, we still have to make a function that calculates the neighborhood.
This is the function that will couple the neighbors. So this is function that this problem is asking you. Well, you can also write another function that does it, but you can also have one function that does the whole thing, you know. So imagine, to write this function, imagine that I'm going to give you some more information because this can be a little abstract maybe. Imagine that you have n birds, and again, you can choose whatever data structure you feel like, but in my opinion, the best thing is that you use a list to store all of the components of your system. So you're going to have a list of x, I, y, I, theta, I, okay? So you have a 3 times n, this is n, and this is 3, okay? So you have a list with the x's, the y's, and the thetas. And these are all of the birds in your system. Given this list, you need to write a function that does the reorientation of the birds. And the tough part here is really this periodic boundary condition thing, okay? This is the tricky part of this problem. So let's break it down in the following way. If you didn't have periodic boundary conditions, so in other words, if you were always in this part of the space, you know what you have to do, right? So if you have a focal xy of the bird you are considering right now, basically, you're going to calculate for all of these birds in the list, you're going to translate these x and y's into a list of distances to bird. This is bird f, I'll call it focal bird. So you will have a list of the distances to f, okay? I'm sure you know how to calculate distances based on positions. And then you just need to mask this list to tell the code the neighborhoods. Okay, let me actually make some order here. The neighborhoods, let's call it NF, the neighborhood of F. If you didn't have periodic boundary conditions, it would just be the list of the distance such that the list of actually the birds, so birds, such as the distances to F is less or equal than R. Okay, This is just the definition of who is in the neighborhood, okay? So if you didn't have periodic boundary condition, this is just a, masking. I'm sure you did hundreds of these exercises when you learned Python or whatever programming languages you use, okay? Now the hard thing is to modify the algorithm to account for periodic boundary conditions. Yes. Do you want me to come or do you want to? Okay.
It's because I just want to be honest here. No, even without the periodic boundary conditions, no, I do not know what to do here.
You don't know what to do here sorry, I couldn't hear properly what you said. Without the periodic boundary conditions, you don't know what to.
Yeah, I don't know what to do even without
okay.
it.
So let me take a step back.
Just properly explain it, because I've only used coding for running statistical analysis. The first contact with actually creating functions for models was in this course.
Right, but
so I do not know how to code something so
But you
complex.
did 1 month. You did now 1 month and a half of coding, right? So now you do have some experience of doing this kind of
but
things.
in the majority of the classes, the teachers would have a skeleton for us in which we had to analyze or complete with fractions of the code, not building it whole from the equation. So I really do not know how to do it.
Yes,
I just want to be honest about it.
Okay, that's fine. So let me actually try to take a step back then. Do you use Python or R?
Mostly R, but we had a Python course as well, so I can adapt to it.
So you know how to mask a list or an array. I believe it's possible in R as well. I don't use it, but it must be possible, okay? Yes. So now, don't, when you approach a technical problem, you should never be psychologically worried about not succeeding. In the end, what you're trying to do is you're just basically trying to do something that you can phrase in words and you understand, and you translate it into machine language, okay? So, you understand what we're trying to do here, or was I not clear on that?
In terms of concepts, it's okay.
Okay, that's already something. So, essentially, from say that this is the focal board and I want to understand, the first thing I need to do to update its direction is to understand who's inside the neighborhood, okay? So that's the first thing I need to do. And to decide who's inside the neighborhood, I need to calculate the distance between this bird, which I call F, to any other bird in the population. So you will calculate the distance to this guy, the distance to this guy, the distance to this guy, the distance to this guy. Okay? So it's just the, the Cartesian metric distance, the usual square root of x squared plus y squared, right? So the distance of this guy. If you have this guy, if you have xf, yf, and you have let's say I, yi. The distance between f and I is just going to be the square root, right? The Pythagoras equation. The square root of xf minus xi squared plus yf minus yi squared, okay? Right? You do this for all of the pairs of birds. Of course, this is a very bad algorithm in terms of computational time, but I mean, there is actually a way to speed it up, but it will be, the algorithm is much harder to code. So this case with n squared, it's fine. We are just here to learn. So you do it for each bird in the population. So you cycle. Well, in fact, in Python, you don't even need to cycle. You can use vectorial operations. I don't know if that's possible in R. So let's say if that you cycle over this list where you have all of your birds, all of your x's and y's, you calculate the distance to f for all of these birds. So now you have a list of distances, okay? And then the neighborhood is just the mask of this array. You just say whomever is at distance fi less than r is the neighborhood, and therefore then you have the list of the birds that are inside the neighborhood. Right? Okay.
It's a bit more clear now.
Okay, great.
Thank you.
Yes. Do you want? Should I come or is it a verbal question? Okay.
What is this capital theta on the equation? It's there is pi and there is the capital theta minus the average of the cosine.
Sorry, 1 second. Let me take it. The capital theta. Where? Sorry.
First, in the first equation, you have theta I in t plus 1 equals the arc of something plus. Yes,
okay.
this.
So this is a Heaviside function.
Oh, okay.
Right. Don't worry about this. So I showed you the solution very briefly. You're just going to write arctan 2 of that, okay?
Okay.
Of the average sine over the average, sorry, the average cosine over the average, the average sine over the average cosine. No, and plus the noise, okay? Because he was confused about the Heaviside theta. Well, and probably many of you are confused about this Heaviside theta part. This is just because the arctangent is a function that is between minus pi half and pi half, okay? It doesn't matter, just use arctan 2, okay? Forget, if you're confused about this, forget about it.
And this arctan 2,
Yes.
it's a NumPy function?
It's a Python function. I believe it exists in R as well.
Okay.
It's a C function. It's originally a C++ function that has this syntax, and I think they kept the same name across many different programming languages.
Okay. Thank you.
How do you want to define the eta for the noise? So we can
The eta will be defined between minus. The noise will be defined between minus eta and eta. But again, this is entirely your choice, okay? It's not like, right? As long as you do something that is consistent, it's fine. And again, you work in groups. I mean, like this is not a test. This is a point where you learn all together something. So you're very welcome to group together and ask each other's and me questions. Yes, Guy. Yes.
I was thinking about how to calculate the periodic
Right.
distance.
Yeah.
So the way that I thought was just make copies of the same plane, and then, for instance, so have a point here and a point here, and then I can make a copy of this one here, and then I can calculate the distance between these two, and just take the
Minimum.
The minimum. Yes.
So this is a possible solution, but it requires writing a lot of code. There is one solution that is much faster and much more compact to write down. So essentially, the first thing you can notice is that, okay, let me actually tell that to everyone, because I think a lot of people is wondering about this. So, this. So I'll start giving you some hints to solve the periodic boundary condition problem, okay? Meaning to extend this algorithm to define a neighborhoods also including the birds that are in the mirror images. One possible solution is to create 4 copies of your square, and then do all of the possible combination of distances. But this is a lot of code, okay? And you're probably gonna miss an if statement when you try to write it up fast. So probably, you know, maybe that's not the best way to go about it. So the first thing you notice when solving this thing is that when you calculate a distance, you essentially, let's say that you have this board here. So this will have a copy here, here, somewhere far away there, and here, okay? Since the distance is a function which is increasing both in the x and y component, you don't actually need to minimize the whole distance. You actually, as long as you find the minimum delta x and the minimum delta y, you're fine, okay? So you can actually separate the problem in finding what is the minimum delta x, delta x prime, and this is delta x, let's say, and this is going to be the same as delta x, right? Because some of these mirror images will be around the y-axis, in which case the delta y's are going to be conserved, and some of these mirror images are going to be around the x-axis, so the delta x's are going to be conserved, okay? So this already reduces a lot the couples that you need to consider, because this delta x is the same as this one. So you're just going to have to consider this delta x prime, this delta y prime, and delta y, okay? Now, this is the first step. This is still not the fastest way to do it. The other thing that you need to realize is that you actually know the size of the box, okay? So basically, you know for sure if you split the box in two, the mirror image is also you can imagine it as a split in two. Therefore, you know for sure that if something is, let's say, farther away than L half than you, some of the mirror images is gonna be closer to you than the actual real bird. So let's take another step into simplifying this. We are considering delta x's and delta y's separately. Therefore, you're going to consider a set of one-dimensional problems. Therefore, essentially, it's as if you are on a circle, and you're that has circumference L. Okay? And you're going, and this has like a boundary that is your boundary, and you're trying to find the fastest way to get to your image on the circle. So topologically, this is what you're doing essentially. And so, using this example, let's say that you have delta x. Can you derive, given what delta x and L are, what delta x prime should be? Delta x, sorry?
So we have 2 points, right? And we can calculate delta x and delta y, the difference between
Right.
the coordinates in each axis.
Right.
So I was thinking that we calculate the minimum between delta x and delta x minus L. The normal delta x minus L, the absolute value.
Okay. You're almost right. You're almost right. You're just missing one thing, but the idea is exactly the right one. So so let me tell you something more. If you knew that all of your focal birds were on the left side of the box, your solution would be exactly right. But you also have birds on the right side of the box. So you need to add one more condition.
So delta x plus L?
Correct. Yes, this is the solution.
Thanks.
Sure. So is this my mic that is doing weird stuff, or is it the other one? Ah, okay. I will explain it in 1 second, yes. Where do I do that? So essentially, okay, you get that we are considering delta x's and delta y's separately right now to simplify the problem. So now I'm gonna explain you the solution for delta x, and the solution for delta y is exactly the same. Okay. So you have 3 possibilities. The first possibility is that delta x is less than L half, in a way, or cell. Okay, but now I'm considering stuff on the left and on the right. Basically, let me actually keep considering this example because I think it's the simplest one. So you have this delta x, and this delta x prime here that I drew here is going to be L minus delta x. Because if you sum delta x and delta x prime, you get exactly L, because this is the mirror image, okay? So you have your delta x prime. These are two of the mirror possibility, and this was the first, in the first solution the Guy gave was to take the minimum between these two, okay? Now, the problem with that is that sometimes your focal bird is on the right side. Sometimes this is going to be your focal bird. And therefore, you're going to have the mirror image of this other bird here, okay? Here, okay? So in this case, you have a delta x prime that is, since your delta x is negative, in the other case, you have delta x prime, which is going to be L plus delta x, which is negative, okay? This delta x prime is going to be L, or if you want, L minus the absolute value of delta x. This is also another possible solution, right? Yes?
But in this case, are we considering that delta x is signed, or is it just like positive?
In this case, it's signed.
Okay.
Yes. Otherwise, you would never have to take the minimum, right? Because it's always bigger than L. So it's always bigger than actually delta x prime.
Yeah, so I think my initial idea was to take in not being signed, like the absolute value of delta x, and
Okay.
minus L, and then take the absolute value of everything.
So you want to do delta x minus L modulo. Is that what you want to take?
Yes, and then take the minimum of this.
Min
with
of this.
delta x.
Minimum of this.
With just delta x, just the absolute value of delta x.
But the minimum over what?
Well, there's this value, the absolute value of L minus the absolute value of delta x. This is a value, and then a second value would just be the absolute value of delta x.
Okay.
The minimum of these two.
Okay. I think so. I think that this can be further simplified. That seems a little hairy. But what you can do is that you realize that you write this down when delta x is positive, and you write this down when delta x is negative. So essentially, you take the minimum of delta x between delta x and L minus the absolute value of delta x, which in a way is very close to what you were thinking, I think, but there is no need to take twice the absolute value. Delta x is never going to be bigger than L.
Yeah.
Right. So this is the most compact solution. So in other words, you do this for, this is going to be your delta x fin. You do this for delta x, you do this for delta y, and you do this inside the list operation where you're calculating distances, so that your distances are going to be already the ones to the closest mirror image. And that defines the neighborhood. I'm taking the absolute value.
Take the absolute value.
Right.
But you need to put the absolute value on the two parts, right? Because then you have something that is not positive.
On the two parts?
Yeah, like minimum.
Sorry, yeah, you're right, of course, yes. No, it's not simple. It requires several steps of simplification. So, I see. So let me show you the solution. Actually, this solution snippet is taking this solution, which is not even the most compact way of writing it down, because I think it's true that this is even shorter. But essentially, if you see, you loop through the birds, because this update rule, you basically need to do it for every bird, okay? Now I ask you to write a function that does it given one bird, but then you're going to have to loop through all of the birds to update all of the population. And then you calculate the delta x and delta y, the final ones, to calculate the neighborhood, as the minimum between delta x in absolute value, the absolute value of L plus delta x, this, and the absolute value of L minus delta x. I actually think that this is even less code, but okay, I mean, it doesn't matter. I mean, you get the idea here. And then once you have this, based on what we said here, which is how we define the neighborhood, you calculate all of the distances to the focal bird and all of the other birds, okay? Already accounting for periodic boundary conditions again. And then you just mask, okay, in this case, the thetas, because remember that your list has 3 entries, the x's, the y's, and the thetas. So in this case, you take directly just the thetas. And you mask them as the radius, the distance less or equal than your parameter r. This is the parameter there. I called it capital R, but here it's called small r. And then you just do this formula, okay? You take the average of the sine of the thetas, the average of the cosine of the thetas. You take this arctan2. Oh no, I erased it, but okay. I told you before, you need to take this arctan2 function for these two values. And then you update as the average plus some noise, okay? Where in this case, eta is between 0 and 2 pi, actually, in this implementation of the code. So you shift it by potentially pi, right? So I will actually upload the solutions in the Google Drive. Let me actually show you though a little bit of the whole code. So okay, this is Python, but hopefully people coding in R can still appreciate it or follow. So okay, this is the function we just discussed. All right. And basically to this function, you just need to add a loop over time and the initialization with some initial conditions and parameters, okay? So I believe that snippets is given in the second challenge problem. If you go to page 5, this gives you the snippet for how to initialize the function that integrates your simulation, basically. So you have a function that takes some parameters and okay, defines some other parameters inside, which is not super elegant, but okay, whatever. You initialize your system with random positions. And then you loop through the time steps, and you save some lists of all of the time steps of all of the position and thetas of the birds. Basically, then you end up having a huge list with all of the thetas, all of the y's for the birds for each time step, okay? So again, this is by far not the most efficient implementation of this thing for many reasons, but just for didactical purposes, we're gonna do it this way. So let me upload So I uploaded the solutions to the lab. If you want to look at them later. I would actually just like to show you a little bit of what I know that, you know, for the first times one coded the spatial algorithm and periodic boundary conditions. This is actually a pretty long, a pretty hard challenge to do in 1 hour and a half. So I mean, it's completely fine if you didn't get through it. But hopefully, I hope that at least I gave you a little bit of the idea behind how you solve for the algorithm of how you do the periodic boundary conditions, okay? Only other thing we didn't talk about related to the periodic boundary conditions is related to the update for the x's and the y's, okay? That's the other part in which you need to be careful. And essentially you just need to do a modulo operation. In math we call a modulo operation when if you go above a certain value, essentially this is going to be I don't know how to call that in English, but whatever is the remaining part of your final thing and the division between your final thing and L in this case. So this is basically just telling the code that if you have a final position at L plus delta x, then the code will give you delta x. This is what a modulo operation does in math, okay? You can also just code if statements and say if x final is bigger than L, then I'm gonna take x final minus L. You can do it. This is the most compact way of writing it down given some Python functions, but you can do it whatever way you want. And if you code it up, and okay, we didn't get there because it's a lot, but you run the simulation, hopefully I find it back. You can create a GIF with a movie, okay? Now this is a little small to see, this is not helping. So now you see, this is a movie. It's all, you have the code in the Jupyter notebook, so you can also see how to create GIFs and movies. So, but basically this is the time evolution of your system, and the little arrows are your birds. Okay? You can also save frames, it's fine. This is just a little cooler to see than saving separate frames at separate time points. So you see that you start your simulation, and then after a while, the arrows are all in the same direction. Remember, this was the point of yesterday's class, that because of the interaction in the system, you just implemented some rules for local interactions or reorientation. Then you end up going all in the same direction. Okay? And you see that when an arrow disappears here, it appears here. Okay? So you have periodic boundary conditions. And so you see that with these parameters, you get everything going in the same directions. If we had more time, this is a lab that at Georgia Tech we run in 3 hours. So once again, don't. It's fine. It's totally fine that we got through a little bit, like through the half of it. It's completely normal. But unfortunately, it's my last day, so I couldn't split it in two. So if you vary the value of the noise, meaning when you reorient yourself, you reorient yourself more or less coherently with the average direction, and you compute the order parameter that we defined yesterday. Therefore, the average direction, so VA is going to be equal to 1 over V0 sample average of all of the V's. Okay, this is the average direction. You reproduce the plot I showed you yesterday. First of all, big noise, you get everything is kind of random. Okay, small noise, after 50 iteration of the code, you get to a situation where everyone is going in the same direction, which is, actually those are the same parameters for the GIF. image. Okay, you can create around with it and create different GIFs for different parameters, but essentially you see that in this simulation it takes little time for them to be going in all of the same direction. If you increase the noise, they will never go in all of the same direction. It's going to be random. Okay. And then if you cycle through different values of the noise, you basically can reproduce the image that Weitz originally did in his PRL paper. I don't remember, in the 90s. I think it's 98. Some of you weren't even born when he wrote that paper. And so you can reproduce this. If one wants, one can try to study the scale-free behavior with a power law fit. Now, this is not what they did because you have finite size effect, but okay, this then gets a little bit tricky. And the last challenge problem in this lab is to actually have informed leaders, okay? Which is what I showed you with the sheep movie yesterday. Remember, there was one sheep that was going in one direction, and then all of the sheeps were going behind the informed sheep. And so basically, this last challenge problem is just to modify this code in order to have a certain amount of birds that will go in the zero theta direction, therefore in the positive x direction. So you will have a certain number of birds that will, no matter what, they will go in this direction. And if you repeat many times these experiments, no, this is the wrong thing. Okay, this is just one realization, but trust me, I tried it, and you can do it several times from random conditions. You end up in a situation where they all go in the direction of the informed individuals, which is in this case the dots. Maybe it's actually easier to see it from here. What's going on here? Yeah. So this is the situation without. So my computer is kind of slow. So in a situation without the informed individuals, they would go all in the same direction, but every time in a different one. Whereas with the informed leaders, they all go always in this same direction, no matter how many times you repeat the experiments. Because the symmetry is not spontaneously broken anymore, and you are breaking it with this input in the model. That's why. So you can continue with the code, but I did want to show you the solutions because I think, it's informative of the fact that you can see it yourselves with code, this emergence of a structure from disorder to order as a function of the parameters. I know it's not super satisfactory that we didn't get there, but you can continue if you're interested in this kind of things. But yes, so we have 7 more minutes, so you can choose whether to continue with the code, or if you have any questions, conceptual, technical about the algorithm, we have some minutes to address them. Okay? Yes. Is it mic, or do I need to come there? Okay. Are you running Python 2 or Python 3?
Not sure.
Because that code is for that's for Python 2. What is it complaining about? What was the error? It's probably just a small syntax thing about some print statement, most likely.
It's saying I think it didn't save all the images, so is that making the
I think it's not finding.
because it saves a lot of images and then compiles them together.
Yes.
So I think it stops saving them. At some point, you just printed one image.
So. Yes, kind of weird. And the error is at line 15.
Exactly where it's saving the picture.
It's the safe fig.
Maybe I tried to write in another compiler.
Are you no? But are you sure the path finds the actual folder you told them?
I'm not sure about that.
Right. So because that's probably the problem, no? I think.
Yeah, but I never. Well,
Do you have in the working directory of this code, you need to have a frames directory. If you don't have it, you need to create it because otherwise the code is not gonna know where to save the images. Yeah. Sure. Are there conceptual questions on the algorithm that is not clear, that someone would like to ask? Other than small bugs or other things like that, if there is something conceptual that is not clear, let me know. Yes.
So, at the end of the day, how do we want our XT to look like? Is like a list of each position of each bird at each time?
Yes, the function will return something like that. It's going to be a fairly big object.
How do I,
Positions and thetas.
yeah, I was wondering like, how do I append like an entire list so that it goes like this instead of just going like
Let me. It's either append or extend. I never remember which one of the two it is. Let me double check. Or the easiest thing is that maybe you pre-allocate the memory in an NumPy array before the simulation, and then you save in the slots the actual thing. That's another possibility, since you already know how many entries it will have at the end. Let me double check what I did here. I don't actually remember. Yes, so I was creating this beforehand. So I was creating an NumPy array with the right dimensions, and then I was just allocating the index entry with the current state. Yes. So just a final note. I know that I know that there are many different approaches in teaching coding. I know that a lot of people have the approach of giving snippets or even just coding in front of you stuff. Everyone has their own style. I personally do not believe in that system, okay? And I know that approaching this other way of doing stuff can be overwhelming. So it's totally fine. And that's kind of the point of it, right? Because until you actually try to do something, you don't learn. So if you're feeling a little bit overwhelmed by this computational lab, it's totally fine. The important thing is that you actually put your hand on a bloody keyboard and you do stuff, okay? rather than sitting there and watching code appearing on a screen. Okay? Then, you know, some people are very efficient in conveying information in that way, and that's perfectly fine. This is just a different approach, okay? So it's just a word of, you know, I know that this is a lot, okay? All right, we're at time, and I think we all would like some coffee now. So please, if you have questions on any part of the course, either computational or theoretical, in both game theory and collective behavior, reach out. I'm going to be here this afternoon after lunch, so you can either come or even afterwards, just send me an email, send me a message on Slack. I don't know if Gabriel is here. No, he's not here. So he asked me a question. I'm going to get back to him about that. But if you have questions about anything, also not related necessarily to the course, and more scientific stuff, you can feel free to reach out, okay? Thank you. Thanks.